Okay, so this is homogeneous linear systems. We're going to look at the system. So last section, we had a solution that looked like this. So what we're going to do is use constant coefficients, and we're going to guess our solution. So again, we're using the same form, and we have seen this before as constant coefficients. V is our constant. It's our vector constant. So in order to plug it in and equate everything, we'll take the derivative of both sides, and we're going to plug it into our system. This gets plugged into the left, and this gets plugged into the right. We'll go ahead and subtract this and get 0 on one side. Factor this out. And we're going to just put the 0 on the right side. Since this can never be 0, and I hope you recognize this, this is how we make our eigenvectors, and it is a dependent system because we assume v doesn't equal to 0, because that would be the trivial solution. And this is exactly our characteristic equation to find our eigenvalues. So here's the theorem. So there's different cases to this. So the eigenvalues are distinct. They're different. Okay, so if all of the lambdas, the eigenvalues, are distinct, well then these are going to form independent solutions, which means it'll form a fundamental set. Okay, so I can prove that, but it's just a one-step proof, and I think that's clear. Let's look at an example. So I know I'm being redundant there, but our x vector is xy, and our x prime vector is x prime y prime. So let's go ahead and find, that's supposed to be 1. Eigenvalues. That's our characteristic equation. So we're going to find our eigenvalue, B1, using, so we're going to plug in 1 into these lambdas to form this. So 2 minus 1 will augment this. So we have x plus y is equal to 0 in our first equation there. Let y equal to t. So then we get x equals minus t, y equals to t. So that xy is minus t, which is minus 1, 1 times t. So my v1 is minus 1, 1. Lambda 2 equals 3, my second one. So that's going to be 2 minus lambda, 2 minus 3. And we'll augment that with 0. If we want, we can even go one more step. Multiply 3 by negative. Not really necessary though. It's our first equation. So my v2. So I do, hold on about that. So our general solution, that was 1, right? Yeah, lambda's 1. So that's our general solution. So this becomes for A. And so now let's find our eigenvalues. And this is our A minus lambda I equals 0, the determinant of it. And I'm going to skip showing all the steps here. But we get lambda 1 equals 0, lambda 2 equals minus 3 with a multiplicity of 2. So they're not distinct. So when we go to solve our eigenvectors, we'll get V0 equals 1, 1, 1. Again, I'm skipping the work here, but we do the same thing. We augment this matrix, plugging in lambda equals 0, augment it with 0 vector. So from this, we actually do get 2 independent vectors. So therefore, we do get 3 independent solutions. So since they're independent, and you can check it using Lonscan if you like, there are 3 independent. These are 2 independent vectors, so all 3 of them independent vectors. And you can just, if you want to double check it using Lonscan, use this. Actually, it doesn't matter. I'll use this one. So this, it's 1. So that's not 0, so therefore it's independent. So our general solution, and that's e to the 0, which is just 1. So it's here that I want to talk about multiplicity. There's 2 types of multiplicity. There is arithmetic multiplicity, AM for short, and geometric, and we'll do GM for short. So AM, the arithmetic multiplicity, is the power of, it's the power of the lambdas, power of the eigenvalues. The geometric multiplicity is how many eigenvalues you get from that. So for example, our lambda 0 above, our AM, we got 1, 0, 1 root, and our GM, we got 1 eigenvalue from it. Our second one, lambda minus 3, the AM, we got 2, and we got out of that 2. So they're both 2 there. And we saw if AM equals GM, we can still find n linear independent eigenvalues. It's not a problem. So that's just the example we just did. As long as it produces the same number of eigenvectors, we're good. Whoops. And I said it wrong here. It's how many eigenvectors. Okay? So one's how many lambdas, the multiplicity of the lambda, and the other is how many eigenvectors it produces. So the question comes about is what if we don't produce enough eigenvectors through the process? So our goal is to find more eigenvectors. So let's look at the process for finding eigenvectors. For V1, for the first vector. So we set up this equation and we solve for v1. So this is for finding the vectors. And then our solutions. And again, this is our normal process. We augment it with 0. And then our solution, our first solution from our first vector is v1, once we find it, e to the lambda 1. So sometimes that produces more than 1, that's fine. But if it doesn't produce more than 1, then to find our second one, we set up this equation. This was already found from part 1. And we can find this, and then we'll just have to solve, that'll be a matrix, and then we'll just have to solve for v2. And then once that happens, our second one, to make it independent, becomes v1 times t plus v2 e to the lambda 2t. It's actually lambda 1 because it's the same one. Now, if it was bigger than this formula goes on. I wouldn't have you calculate it by hand more than once right here. But our third one, to find v3, it's a minus lambda I, v3 equals v2. But this is where it gets a little bit more complicated. And I'm not showing how to derive this, but it's not too hard to do. And so on and so on. So let's do an example. So let's go ahead and find our eigenvalues. So I forgot to subtract lambda. Okay, so we have our multiplicity of 2, which we expected. And so we plug in the normal way, a minus lambda I x equals 0, solve for it. I'm just going to go ahead and augment that. That's the same. This is the same a minus lambda I, but determinate. So here we'll augment it. We're plugging in negative 1. And like I said, we're augmenting. And this matrix, by the way, is always, as I mentioned earlier, a dependent. So you should always get it's a dependent. It's dependent, so you should always get a row of zeros. I'm going to divide by 2. Multiply by 2 on the bottom, add it. And then we get the first row. Okay, so our v1 is the vector minus 2, 1. You could have 2 minus 1, it works out the same. You can see here we can multiply through by negative. Just change it so you can see it doesn't matter. If you have fractions here, you can also clear it, but you got to be careful with some of the stuff we're doing today. And this is our eigenvalue. Right, this is our eigenvector. And so since it only produced one, those are the same, by the way. Our second eigenvector, we have to use the formula. It's A minus lambda I times V2. We're trying to find, and we put in V1 there. So A minus lambda I, again, it's the same lambda. So it's going to be this. So it's 2, 4, minus 1, minus 2. My V2 I'm looking for, and my V1 I just found, 2 minus 1. And to solve this, we augment it, not with 0, but with that V1. You can use Kramer's too if you like. I'll divide the top row by 1. Multiply through by so we have this equation here. X plus 2y is equal to 1. So we'll set y is equal to t, like we did last time, and x equals 2 minus 2t plus 1, using that equation. I'm plugging in t. If we want, doesn't matter. 1 minus 2t looks prettier, maybe. So our general solution, so that's my x, that's my y, which is t. And so my V2, I should finish this off, is 1 minus 2t times t. We can leave it like that, or we can go further. I'll do both ways. Let's just keep it that way for now. So my general solution is x equals c1, 2 minus 1, e to the minus t, plus c2, 1 minus 2t, t to e to the minus t. I'll box that, but I'm going to show you we can take this a little further to get that formula that we had up there. So as I mentioned, this can be written out a little further. Could be C2, 1, and then copy this in the front. And so as I mentioned before, this was my solution for my second one. Do realize that this is my V1, which is my V1 times t right here. And this right here is my V2, or my V2 is 1 minus 2t times t. When I set t equal to 0, you get V2 equals to 1, 0. Okay? You could plug in any value for t. But either way is acceptable as an answer. That's it.